Hello there, and welcome to The Sleeping Scientist. I'm so glad you found your way here. Maybe you had a long day, or maybe you're the kind of person who likes falling asleep to deep thoughts and cosmic mysteries rather than counting sheep. Either way, tonight's journey is for you. You've got nothing to do but rest. Let your mind relax, your breathing slow, and your body grow light as if gravity itself has softened. Because tonight, we aren't simply stargazing. We're drifting through our galactic home, the Milky Way, discovering secrets hidden in starlight and shadow. Let's begin. Picture yourself floating above Earth, rising higher and higher until the blue marble shrinks to a pinpoint. You're moving outward now, past the Moon, past Mars, beyond the orbit of distant Neptune. Keep going. The Sun becomes just another star, and suddenly you see it. A river of light stretching across the darkness. Billions upon billions of stars arranged in graceful spiraling arms, all rotating slowly around a luminous center. This is our galaxy, our cosmic address. And it's far stranger than you might imagine. The Milky Way stretches approximately 100,000 light years from edge to edge. That's the visible disk anyway, the part we can see with optical telescopes. 1 light year equals about 6 trillion miles. The distance light travels in a year, moving at 186,000 miles per second. So, when we say the galaxy is 100,000 light years across, we're talking about a span so vast that light itself takes 100 millennia to cross it. Even traveling at the speed of a commercial jet, you'd need more than 100 billion years to fly from one side to the other. The universe isn't even that old yet, but here's something that surprised astronomers. The galaxy doesn't end where the visible disk stops. Surrounding everything we can see is an enormous halo, a spherical cloud of gas, old stars, and something else entirely. This halo extends outward to nearly 1 million light years from the center. When you include it, the Milky Way is actually closer to 2 million light years across. Twice the size we once thought. Most of this halo remains invisible to conventional telescopes, revealed only through careful measurements of how its gravity affects other objects. The galaxy's disk isn't uniformly thick either. It varies depending on what you're measuring. The thin disk, where most star formation happens today, is only about 1,000 light years thick. That might sound substantial until you remember the disk stretches 100,000 light years wide. Proportionally, it's thinner than a sheet of paper. The thick disk, home to older stars, extends a bit further vertically, and threading through all of it, connecting everything, is the interstellar medium, a tenuous mixture of gas and dust that fills the spaces between stars. How many stars call this structure home? Estimates vary considerably. Our galaxy probably contains somewhere between 200 and 400 billion stars. Some calculations push toward the higher end of that range. Others suggest numbers closer to 200 billion. The uncertainty stems from how difficult it is to count stars when you're embedded inside the very thing you're trying to measure. It's like asking someone to count all the trees in a forest while standing in the middle of it, surrounded by fog. Many stars hide behind clouds of dust. Others are too faint to detect at great distances, and countless more lurk in the crowded central regions where individual stars blur together. From Earth on a clear dark night, far from city lights, you might see about 3,000 stars with your unaided eyes. 3,000 out of hundreds of billions. It's a humbling fraction. Every point of light you've ever seen in the night sky, every constellation ancient civilizations named, every star that's guided sailors across oceans, all of them together represent less than 1/1,000,000th of 1% of the galaxy's stellar population. The rest remain invisible, too distant or too dim, their light lost in the vastness. These stars aren't all the same age. The galaxy contains multiple generations, each with its own story. In the disk, you'll find younger stars, what astronomers call population 1 stars. These orbit the galactic center along relatively circular paths confined to the flat plane of the disk. They formed from gas enriched by previous stellar generations, so they contain higher proportions of heavy elements. Iron, carbon, oxygen, all the atoms heavier than hydrogen and helium that astronomers collectively call metals, even though many aren't metals in the chemical sense. But venture into the halo, that vast spherical region surrounding the disk, and you'll encounter a different kind of star entirely. These are population 2 stars, ancient objects that formed when the galaxy was young. They orbit the center along random, tilted paths that take them high above and below the galactic plane. Their chemical composition tells a story of an earlier universe. They contain far fewer heavy elements than their younger cousins in the disk. Some are so metal-poor that they must have formed when the cosmos was still pristine, before many generations of stars had manufactured and scattered heavier atoms. Scattered throughout the halo, you'll also find globular clusters. These are tight spherical collections of hundreds of thousands of stars, all orbiting together. Some globular clusters are among the oldest objects in the galaxy, nearly as old as the universe itself. They're fossil relics from the Milky Way's youth, survivors from a time when galaxy formation was chaotic and violent. The disk itself shows color variations when viewed from a distance. In images and simulations, it appears bluish, especially in the spiral arms. This blue tint comes from massive, hot, young stars that burn intensely but briefly. These O and B type stars emit tremendous amounts of ultraviolet and blue light. They're short-lived compared to smaller stars, existing for only millions of years before exploding as supernovae. But because they're so luminous, they dominate the appearance of the regions where they form. The central bulge presents a different palette. It glows yellowish or reddish, reflecting its population of older, cooler stars. Red giants and red supergiants populate this region, stars in their twilight years that have swollen to enormous sizes and cooled to lower surface temperatures. They cast a warmer light, giving the galaxy's heart its characteristic color. At the very center lies something even more remarkable. A supermassive black hole. Astronomers call it Sagittarius A star, abbreviated as SGRA star. This isn't a theoretical object or a mathematical abstraction. It's real, confirmed by decades of painstaking observations. Scientists have watched individual stars orbit around this invisible point, tracing elliptical paths at tremendous speeds. From these orbital dynamics, they've calculated the mass of whatever sits at that location. The answer? Approximately 4.3 million times the mass of our Sun, all compressed into a region smaller than our solar system. The black hole was first detected in the 1970s as a radio source, a bright spot in radio wavelengths emanating from the galactic center. But proving it was a black hole required watching stars move around it. Reinhard Genzel and Andrea Ghez spent years doing exactly that, tracking stellar orbits with ever-improving telescopes. Their work earned them a share of the 2020 Nobel Prize in Physics for demonstrating that Sagittarius A star could only be a supermassive black hole. No other explanation fit the observations. The black hole sits about 26 to 27,000 light-years from Earth in the direction of the constellation Sagittarius. That's why we can't see it directly in visible light. Too much dust and too many stars lie between us and the galactic center. But in May 2022, the Event Horizon Telescope collaboration released something extraordinary, an actual image of Sagittarius A star, or rather, an image of its shadow, the dark silhouette of the event horizon surrounded by a glowing ring of superheated gas spiraling inward. Surprisingly, Sagittarius A star is relatively quiet for a supermassive black hole. It consumes matter slowly, accreting gas and occasional stars at a leisurely pace. Many galaxies have far more active central black holes that shine brilliantly as they devour vast amounts of material. But ours seems to be sleeping, or at least it's sleeping now. Recent observations from NASA's IXPE telescope suggest the black hole woke up about 200 years ago, briefly devouring nearby material before settling back into quiescence. We're seeing the afterglow of that ancient feast, light and high-energy particles still echoing through the surrounding gas clouds. The Milky Way isn't a simple spiral galaxy. It's classified as a barred spiral, meaning it has a prominent bar-shaped structure of stars extending from the central bulge. From the ends of this bar, the spiral arms emerge, curving outward in graceful arcs. The bar wasn't always recognized as part of our galaxy's architecture. Astronomers only began suspecting its existence in the 1960s, and confirmation came even later. The problem was perspective. When you're inside the galaxy, embedded in the disk, seeing the overall structure is incredibly difficult. The bar plays a crucial role in galactic evolution. It acts like a gravitational highway, channeling gas from the outer regions toward the center. This feeds the central black hole and triggers star formation in the inner galaxy. The bar contains roughly 30 to 40% of all stellar mass in the galaxy, a significant fraction concentrated in a relatively small region. It rotates too, though not quite as fast as the disk material around it. This differential rotation creates complex gravitational interactions that help maintain the spiral arm structure. Speaking of spiral arms, the Milky Way has at least 4 major ones. The Perseus arm and the Scutum Centaurus arm are the 2 most prominent. Then there are 2 less pronounced arms, or spurs, the Sagittarius arm and the Local arm. Our solar system resides in that local arm, also called the Orion spur, positioned roughly halfway between the Perseus and Sagittarius arms. We're in a relatively quiet neighborhood, far from the intense star formation and violent stellar deaths that characterize the main spiral arms. These arms aren't solid structures. They're not like spokes on a wheel, fixed and rigid. Instead, they're regions of enhanced density, areas where stars, gas, and dust temporarily crowd together. Think of them as galactic traffic jams. Stars drift into the arms, linger for a while as the density wave passes through, then drift out the other side. The arms themselves rotate around the galaxy, but at a different speed than individual stars. This creates the appearance of a stable spiral pattern, even though the individual components are constantly moving. Recent research suggests these spiral arms might be more temporary than astronomers once believed. They may exist for only 80 to 100 million years before dissolving and reforming. That's a small fraction of the galaxy's 13 billion year lifetime. The arms may come and go, shaped and reshaped by gravitational interactions, infalling satellite galaxies, and the internal dynamics of the disk itself. Our Sun orbits the galactic center at considerable speed. Just as Earth orbits the Sun, the entire solar system orbits the center of the Milky Way. One complete orbit takes approximately 225 million Earth years, a span sometimes called a cosmic year. Since Earth formed about 4.5 billion years ago, our planet has completed roughly 20 trips around the galaxy. 20 cosmic years. During the age of dinosaurs, we were in a completely different part of the galaxy. The stars visible in their night sky, if dinosaurs had looked up, would have been entirely different from the ones we see today. The Sun doesn't travel in a perfectly flat circle either. It oscillates up and down through the galactic plane as it orbits, crossing through the disk about 2.7 times per orbit. Right now, we're only about 95 light years from the central plane, practically sitting right in the middle of the disk. This bobbing motion takes us through regions of varying density and radiation, potentially influencing Earth's climate and biological history over very long timescales, though the effects remain uncertain and debated. Our location between the major spiral arms might not be accidental. Regions closer to the galactic center experience higher levels of radiation from the densely packed stars and the active black hole. The spiral arms themselves host frequent supernova explosions and intense stellar radiation that could be hazardous to developing life. Here in the Orion spur, we're in a relatively calm zone, a galactic safe haven where life had time to emerge and evolve without too much cosmic interference. The European Space Agency's Gaia mission has revolutionized our understanding of the Milky Way's structure and dynamics in ways that would have seemed impossible just a few decades ago. Launched in 2013, Gaia spent over a decade precisely measuring the positions, distances, and motions of more than 2 billion stars. 2 billion individual stellar measurements, 3 trillion observations in total. The resulting catalogue represents the most detailed map of our galaxy ever created. Gaia completed its primary observational mission in early 2025, though scientists will be analysing its data for years to come. The spacecraft is now being moved to a retirement orbit, its active mission complete. But the legacy of Gaia will shape astronomy for generations. 2 massive final data releases are planned, one around 2026 and another near the end of the decade. These will contain even more refined measurements and discoveries. What has Gaia revealed? The galaxy's disk isn't flat. It's warped, twisted, and rippling in ways we didn't fully appreciate before. One side curves upward relative to the galactic plane, the other curves downward. The disk resembles the brim of a hat, flexing and wobbling over time. This warping was suspected since the 1950s, but Gaia showed that the warp slowly precesses, like a spinning top wobbling as it rotates. Even more remarkably, Gaia discovered an enormous wave structure moving through the galaxy. It's like dropping a pebble in a pond and watching ripples spread outward. Except this wave extends across tens of thousands of light years and affects the motions of millions of stars. The wave stretches from about 30,000 to 65,000 light years from the galactic center, influencing stars far from the sun. What caused this wave? Possibly a past encounter with a satellite galaxy, or perhaps internal gravitational dynamics within the disk itself. Scientists are still working out the details. Gaia also revealed evidence of ancient collisions. The Milky Way didn't form in isolation. It grew through mergers with smaller galaxies over billions of years. Gaia's precise measurements let astronomers trace stellar motions backward in time, identifying groups of stars with similar orbits and chemical compositions. These stellar streams are the remnants of smaller galaxies that merged with the Milky Way long ago. One major merger event, sometimes called the Gaia-Enceladus merger, occurred roughly 10 billion years ago and contributed significantly to the formation of our galactic halo. Perhaps most exciting, Gaia has discovered new objects hiding in plain sight. It found a black hole with a mass nearly 33 times that of the Sun, less than 2,000 light years from Earth. This was the first time a stellar origin black hole this massive had been spotted within the Milky Way. It's hiding in the constellation Aquila, invisible except for its gravitational influence on a companion star that Gaia detected orbiting the void. The mission also catalogued thousands of brown dwarfs, objects too small to sustain hydrogen fusion but larger than planets. It discovered new exoplanets through the subtle wobbles they induce in their host stars. It even tracked asteroids within our own solar system, demonstrating its versatility. Gaia didn't just map the Milky Way. It opened our eyes to a dynamic, evolving structure far more complex than we imagined. As you drift towards sleep tonight, picture yourself floating in that river of stars. The Milky Way stretches above and below, to all sides, a slowly rotating disk of light, punctuated by dark lanes of dust. Spiral arms curve through the darkness like frozen waves. At the center, invisible but present, a supermassive black hole holds everything together through gravity's patient grip. And somewhere in a quiet arm between the major structures, a yellow star orbits peacefully, carrying a small blue planet where life emerged and learned to look upward, wondering about its place in the cosmic dance. The galaxy continues its ancient rotation, stars drifting along their paths, gas clouds collapsing to form new suns, old stars dying and scattering their enriched ashes back into space. It's a cycle that's been running for over 13 billion years, and it will continue long after we're gone. But for now, in this moment, we're here to witness it, part of the galaxy looking back at itself. The space between stars isn't empty. That's one of those things you might assume if you picture space as a void, but the truth is far more interesting. Between every star in the Milky Way, stretching across those vast distances we can barely comprehend, there's material, gas, mostly hydrogen, along with dust grains so fine they'd slip through your fingers if you could somehow hold them. This interstellar medium, as astronomers call it, is where new stars are born. Think about that for a moment. The very substance that fills the gaps between stars is also the raw material for future suns. It's a cycle that's been running since the galaxy formed, over 13 billion years ago. Stars are born from collapsing clouds of gas. They live for millions or billions of years, fusing hydrogen into heavier elements in their cores. Then they die, either quietly or explosively, scattering those heavier elements back into space. That enriched material mixes with the existing interstellar medium, and eventually gravity pulls it together again to form new stars. Each generation is slightly richer in heavy elements than the last. The interstellar medium isn't uniformly distributed. Some regions are incredibly dense, with particles packed relatively close together by cosmic standards. These are molecular clouds, vast structures that can span hundreds of light years and contain enough material to form thousands of stars. Other regions are much more diffuse, with only a few atoms per cubic centimeter. To put that in perspective, the air you're breathing right now contains about 10 to the 19th power molecules per cubic centimeter. The thinnest parts of interstellar space have maybe one atom in the same volume. It's a vacuum better than anything we can create in laboratories on Earth. But here's what makes it fascinating. Even in those incredibly empty regions, things happen. Atoms collide occasionally. Photons from distant stars pass through. Cosmic rays zip along at nearly the speed of light. The interstellar medium isn't static. It's constantly stirred by stellar winds, supernova explosions, and the rotation of the galaxy itself. Shockwaves from dying stars compress nearby gas, triggering collapse and star formation. The magnetic fields threading through space guide the motion of charged particles. It's a dynamic, evolving environment, even if it looks empty to our eyes. Some of the most beautiful objects in astronomy are regions where the interstellar medium glows. Nebulae, those colourful clouds you've probably seen in space photographs, are places where ultraviolet light from hot young stars ionizes the surrounding gas, causing it to emit light at specific wavelengths. The Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, is one such region. Inside that glowing cloud, new stars are forming right now, coalescing from the surrounding material. In a few million years, they'll emerge from their dusty cocoons and begin their long lives as main sequence stars. The dust component of the interstellar medium plays a crucial role in star formation. These tiny grains, typically less than a micrometer across, are made of materials like carbon, silicon, and iron compounds. They form in the atmospheres of dying stars and are scattered into space. Dust grains absorb visible light, which is why dense clouds appear dark against the background stars. But they also radiate in the infrared, and infrared telescopes can peer through these clouds to see what's happening inside. Without dust, we'd miss most of the star formation in the galaxy. Dust grains also serve another purpose. In the coldest regions of molecular clouds, molecules can form on the surfaces of dust grains. Simple molecules like carbon monoxide and water ice accumulate in thin layers. More complex organic molecules have been detected too, including amino acids, the building blocks of proteins. This doesn't mean life is forming in interstellar space, but it does suggest that some of the chemistry necessary for life can occur in these cold, dark clouds long before planets form. When a new solar system eventually coalesces from this material, it inherits a chemical legacy from the interstellar medium. Radio astronomy has been essential for studying this hidden realm. Radio waves penetrate dust clouds easily, and many molecules emit radiation at specific radio frequencies. By tuning to these frequencies, astronomers can map the distribution of different molecules throughout the galaxy. Neutral hydrogen, the most abundant element, emits radiation at 21 centimeters. This wavelength is long enough to travel through dust without being absorbed, so radio telescopes can detect hydrogen throughout the entire galaxy, even on the far side of the galactic center, where optical telescopes see nothing but darkness. These radio observations revealed the spiral structure of the Milky Way. By mapping where hydrogen gas is concentrated, astronomers could trace out the spiral arms. The gas is denser in the arms, compressed by density waves that sweep through the disk. Stars form preferentially in these compressed regions, which is why the spiral arms appear bright in photographs of other galaxies. We can't take a picture of our own galaxy from outside, but radio observations give us the next best thing: a map of where material is concentrated and where stars are likely forming. The temperature of the interstellar medium varies dramatically depending on what's heating it. In dense molecular clouds, temperatures can drop to just 10 or 20 degrees above absolute zero. These are the coldest places in the galaxy, shielded from starlight by thick layers of dust. At the other extreme, regions heated by supernova shockwaves or intense ultraviolet radiation can reach millions of degrees. This hot gas is so diffuse it's nearly invisible, but it exists in vast bubbles carved out by stellar activity. X-ray telescopes can detect it, revealing a hidden structure of superhot cavities and filaments. What you're hearing now, the facts about interstellar medium, might seem abstract, but this material is personal in a way that's easy to overlook. Every atom in your body, except hydrogen, was forged inside a star. The calcium in your bones, the iron in your blood, the carbon that forms the backbone of every organic molecule within you, all of it came from stellar nucleosynthesis. Stars created these elements, then returned them to space when they died. That material mixed into the interstellar medium was incorporated into a new generation of stars and planets, and eventually became part of Earth and everything on it, including you. Carl Sagan famously said, "We are made of star stuff." It's not just poetic, it's literally true. The atoms that make up your body right now have been through multiple cycles of stellar birth and death. They've drifted through interstellar space, been compressed in molecular clouds, accreted onto planets, and somehow ended up arranged in a pattern that can think and wonder about the universe. When you look up at the Milky Way on a dark night, you're not just looking at distant suns, you're looking at the material from which you came and to which you'll eventually return. The interstellar medium also plays a role in regulating star formation. If gas collapses too quickly, stars would form at a much higher rate than we observe. Something must be slowing the process down. Part of the answer is turbulence. The interstellar medium isn't smoothly distributed, but filled with swirls and eddies, like a cosmic ocean in constant motion. This turbulence provides support against gravitational collapse, preventing clouds from collapsing until they reach a critical density. Magnetic fields also contribute, threading through the gas and providing additional resistance to collapse. Star formation is inefficient by cosmic standards. Only a small percentage of the gas in a molecular cloud actually ends up in stars. The rest is either blown away by stellar winds and radiation from the newly formed stars, or it remains as diffuse gas between the stars. This inefficiency is actually important for the long-term evolution of the galaxy. If all the gas collapsed into stars at once, the galaxy would burn out quickly, exhausting its fuel in a burst of activity. Instead, star formation proceeds slowly over billions of years, maintaining a steady population of stars across multiple generations. There's also a feedback loop at work. Massive stars, the ones that burn brightest and die youngest, inject enormous amounts of energy into their surroundings through stellar winds and supernova explosions. This energy heats the surrounding gas and can even blow it out of the galaxy entirely in some cases. The heated gas takes a long time to cool down and settle back into star-forming clouds. This self-regulation keeps the star formation rate relatively stable over time. The galaxy produces new stars, but not so many that it exhausts its fuel supply too quickly. In recent years, astronomers have discovered that gas doesn't just cycle within the galaxy. Fresh material falls in from outside, accreted from the cosmic web, the large-scale structure of the universe where galaxies form along filaments of dark matter and gas. This inflow replenishes the interstellar medium, providing raw material for future star formation. The Milky Way isn't a closed system. It's constantly exchanging matter with its surroundings, growing slowly through accretion, while also losing some material to galactic winds. The study of the interstellar medium connects to almost every other area of galactic astronomy. You can't understand star formation without understanding the properties of the gas clouds where stars are born. You can't understand chemical evolution without tracking how elements are synthesized in stars and returned to space. You can't understand the structure of the galaxy without mapping where material is concentrated. The interstellar medium is the connective tissue of the galaxy, the medium through which everything else happens, and it's beautiful in its own way. Not in the obvious sense of glowing nebulae, though those are stunning, but in the subtlety of it. The idea that space isn't empty, but filled with potential. That the gaps between stars contain the seeds of future solar systems. That the atoms scattered thinly across these vast distances will someday, given enough time and the right conditions, come together to form something new. A star, a planet, perhaps even life. As you drift towards sleep tonight, imagine yourself floating in one of those dense molecular clouds. It's dark. Starlight is blocked by dust, but it's not cold in an uncomfortable way. It's just quiet, peaceful. Around you, invisible to your eyes, hydrogen molecules drift slowly. Dust grains tumble through the void. Somewhere nearby, a region is beginning to collapse under its own gravity. In a few 100,000 years, it will ignite as a new star. But for now, it's just potential. Just matter following the laws of physics, drifting through the dark. The interstellar medium reminds us that emptiness is relative. What looks like void from a distance is actually full of material, energy, and possibility. The universe isn't divided neatly into stars and empty space. There's a whole realm in between, a vast ecology of gas and dust that shapes everything we see. The next time you look up at the night sky and see the band of the Milky Way stretching overhead, remember that the dark lanes cutting through it aren't empty. They're dense clouds of material, regions where future stars are gestating. The darkness is just light blocked by dust. Behind it, creation is ongoing. Now let's talk about something equally invisible but even more mysterious. Something that makes up most of the mass of the galaxy but has never been directly detected. Dark matter. You've probably heard the term before. It shows up in documentaries and science articles, often described as one of the greatest unsolved mysteries in physics. And it is. But what exactly is it? And how do we know it exists if we can't see it? The story begins with galactic rotation. In the 1930s, astronomer Fritz Zwicky was studying galaxy clusters, groups of galaxies bound together by gravity. He measured how fast individual galaxies within these clusters were moving and used those velocities to estimate the total mass of the cluster. The result didn't make sense. The visible matter, all the stars and gas he could observe, wasn't nearly enough to account for the motions he measured. The galaxies were moving too fast. They should have escaped the cluster's gravitational pull long ago, unless there was additional mass holding them in place, mass that wasn't visible. Zwicky called this unseen material dark matter. At the time, most astronomers dismissed the idea. They figured there must be an error in the observations or the calculations. But decades later, astronomer Vera Rubin found similar evidence in individual spiral galaxies. She measured how far stars orbit the centers of these galaxies at different distances. According to Newton's laws of gravity, stars farther from the center should orbit more slowly, just like how Neptune orbits the Sun more slowly than Earth does. But that's not what Rubin found. Stars in the outer regions of galaxies orbit just as fast as stars closer to the center. The rotation curves are flat, not declining. This only makes sense if the galaxy contains much more mass than we can see, distributed in a large halo extending far beyond the visible disk. The stars and gas we observe are just the tip of the iceberg. Most of the galaxy's mass is invisible. Additional evidence comes from gravitational lensing. According to Einstein's theory of general relativity, mass bends space, and light follows the curvature of space. When light from a distant galaxy passes near a massive object like a galaxy cluster, its path is bent, creating distorted or multiple images of the background galaxy. By analyzing these distortions, astronomers can map where mass is concentrated in the foreground cluster. Time and again, these maps show more mass than can be accounted for by visible matter. The lensing is too strong unless dark matter is present. So what is dark matter? That's the trillion-dollar question. It's not ordinary matter like protons, neutrons, and electrons. We know that because ordinary matter interacts with light. Even if it's dark, like a black cloud of gas, it would absorb light and reveal itself through absorption lines in spectra. Dark matter doesn't do this. It doesn't emit, absorb, or reflect electromagnetic radiation at any wavelength. It only interacts through gravity. One possibility is that dark matter consists of exotic particles that have never been detected in laboratories. Physicists have proposed various candidates. WIMPs, weakly interacting massive particles, are a popular option. These hypothetical particles would have mass but interact with ordinary matter only through gravity and possibly the weak nuclear force. Experiments deep underground have been searching for WIMPs for decades, hoping to catch one colliding with an atomic nucleus. So far, no confirmed detections. Another candidate is axions, much lighter particles that could exist in enormous numbers. Or dark matter might be something even stranger, particles or entities we haven't thought of yet. The truth is, we don't know. Dark matter remains one of the most profound mysteries in science, a reminder that despite all our progress, we still don't understand what most of the universe is made of. What we do know is that dark matter shaped the formation of galaxies. In the early universe, dark matter began clumping together under its own gravity before ordinary matter did. These dark matter halos provided gravitational wells into which ordinary matter, hydrogen and helium gas, could fall. The gas accumulated in these wells, eventually reaching densities high enough for star formation to begin. Galaxies formed inside dark matter halos. Without dark matter, the universe would look completely different. Galaxies as we know them might not exist at all. The Milky Way is embedded in a dark matter halo that extends far beyond the visible disk. This halo is roughly spherical and contains maybe 10 times more mass than all the stars, gas, and dust combined. We can't see it directly, but its gravitational influence shapes the orbits of stars throughout the galaxy. The Sun, orbiting 26,000 light-years from the center, is moving through this dark matter halo right now. Dark matter particles, whatever they are passing through Earth constantly. Through you as you lie here listening. That might sound unsettling, but it's harmless. If dark matter interacts with ordinary matter at all, it does so incredibly weakly. Trillions of dark matter particles could pass through your body every second without a single interaction. You'd never notice. The entire Earth is transparent to dark matter. It passes through as if we weren't here. Some alternative theories propose that dark matter doesn't exist at all. Instead, they suggest our understanding of gravity might be incomplete. Perhaps gravity behaves differently on galactic scales than we think, and the anomalous rotation curves are due to modified physics rather than unseen mass. These theories, collectively called MOND, modified Newtonian dynamics, have had some success explaining certain observations, but they struggle with others, particularly gravitational lensing and the cosmic microwave background. So far, dark matter remains the leading explanation, even though we don't know what it is. The search continues. Experiments around the world are trying to detect dark matter particles directly. Others are looking for signs of dark matter annihilating or decaying, which might produce faint signals of gamma rays or other radiation. The Large Hadron Collider attempts to create dark matter particles in high-energy collisions. Someday, one of these efforts might succeed, or we might discover that dark matter is something entirely unexpected, something that changes our understanding of physics at a fundamental level. For now, it remains a mystery, a presence felt but never seen, holding galaxies together through invisible threads of gravity. Beyond the dark matter halo, beyond even the most distant visible stars, the Milky Way continues in ways we're only beginning to understand. The galaxy we inhabit extends far beyond what we can see with our eyes, or even our most powerful optical telescopes. It's a structure built in layers, like an onion, each layer telling a different story about how galaxies form and evolve over cosmic time. The visible disk, that flat collection of stars and gas we picture when we think of the Milky Way, is just the beginning. Surrounding it is the thick disk, containing older stars with more random orbits. Beyond that lies the stellar halo, a roughly spherical cloud of ancient stars and globular clusters. And enveloping everything is the dark matter halo, extending perhaps 2 million light-years from the center. The Milky Way is far larger than it appears. Recent measurements suggest the galaxy's true boundary might be defined by where its gravitational influence ends, where its pull gives way to the gravity of neighboring galaxies. That boundary lies somewhere around 1 million light-years from the center, making our galaxy's total diameter roughly 2 million light-years across. That's 20 times wider than the visible disk. Most of the Milky Way is invisible, composed of dark matter and scattered ancient stars drifting through the darkness. The stellar halo contains some of the galaxy's oldest inhabitants. These are stars that formed when the universe was young, when there were almost no heavy elements yet. They're called population 2 stars, metal poor compared to younger stars like our Sun. Some of these halo stars are over 13 billion years old, nearly as ancient as the universe itself. They orbit the galactic center on paths tilted at random angles, not confined to the disk like younger stars. Their orbits carry them high above and far below the galactic plane, lonely wanderers in the cosmic dark. Embedded within the halo are globular clusters, dense spherical collections of hundreds of thousands of stars. The Milky Way has over 150 known globular clusters, and they're spectacular objects. In a globular cluster, stars are packed so tightly that if you lived on a planet in one, your night sky would be ablaze with thousands of bright stars, many closer than the nearest star to our Sun. These clusters are ancient, most formed over 10 billion years ago. They're fossil remnants from the galaxy's youth, preserved through cosmic time. The existence of these old halo stars and globular clusters tells us something important about how the Milky Way formed. The galaxy didn't appear all at once, fully formed like it is today. Instead, it assembled gradually from smaller pieces. In the early universe, small proto-galaxies formed first. Over time, gravity pulled them together. They merged and combined, building larger galaxies. The Milky Way grew through this process, consuming smaller galaxies and incorporating their stars. We can still see evidence of this ongoing process today. The Milky Way is currently in the process of absorbing several smaller satellite galaxies. The most dramatic example is the Sagittarius Dwarf Elliptical Galaxy. a small galaxy that's being torn apart by the Milky Way's gravity. As it orbits, tidal forces stretch it into long streams of stars that wrap around our galaxy. These stellar streams are like cosmic fossils, traces of galaxies that no longer exist as distinct objects. The Gaia spacecraft has been instrumental in discovering these streams. By precisely measuring the positions and velocities of billions of stars, Gaia can identify groups of stars moving together through space, stars that share a common origin. Many such streams have been found, each one the remnant of a small galaxy consumed by the Milky Way. Every stream is a chapter in our galaxy's history, a story written in starlight. One particularly significant merger happened roughly 10 billion years ago. Astronomers call it the Gaia-Enceladus merger. A dwarf galaxy, perhaps 1/4 the mass of the Milky Way at the time, collided with our galaxy. The collision was violent by galactic standards, though it happened over hundreds of millions of years. The impact disrupted the existing disk, scattered stars into the halo, and may have triggered intense star formation. Today, a large fraction of the Milky Way's halo stars are thought to be remnants of this ancient collision. The history of galactic mergers raises an interesting question about the future. The Milky Way is part of a collection of galaxies called the Local Group, which contains over 50 galaxies. The two largest members are the Milky Way and the Andromeda Galaxy, also known as M31. Andromeda is the nearest large galaxy to us, located about 2.5 million light-years away, and it's heading in our direction. Astronomers have known for decades that Andromeda and the Milky Way are on a collision course. Observations show Andromeda's light is blue-shifted, meaning it's moving toward us. The two galaxies are approaching at about 110 kilometers per second. Given their separation and velocities, calculations suggested a collision would occur in roughly 4.5 billion years. The merger would be spectacular, reshaping both galaxies completely, eventually forming a single giant elliptical galaxy, sometimes nicknamed Milkomeda. But recent research has complicated this picture. New calculations using the latest data from Gaia and Hubble suggest the collision isn't as certain as we thought. When you account for the gravitational effects of other nearby galaxies, particularly the Large Magellanic Cloud and the Triangulum Galaxy, the trajectory becomes less clear. These additional gravitational pulls can alter the paths of both the Milky Way and Andromeda. Current estimates now give only about a 50% chance that the two galaxies will actually collide within the next 10 billion years. There's a possibility they might pass by each other instead, close enough to distort each other gravitationally, but not merging completely. Or the collision might happen much later than previously predicted. The future, it turns out, is harder to predict than we realized. The universe is complex, with many factors influencing how galaxies move through space. Even with our most precise measurements and sophisticated models, uncertainty remains. If a collision does happen, what would it look like? From a distance, it would be a slow-motion cosmic dance spanning hundreds of millions of years. The two spiral galaxies would approach, their gravity distorting each other. Long tidal tails of stars would stream outward into space. The spiral arms would become twisted and disrupted. Eventually, the two central bulges would merge, combining their supermassive black holes into a single, even more massive black hole. Star formation would spike dramatically as gas clouds collided and compressed. The night sky would blaze with newborn stars. But here's something reassuring. Even during a galactic collision, individual stars almost never collide. Space is mostly empty. Stars are tiny points separated by vast distances. The chance of our Sun colliding with another star during the Andromeda merger is negligible. The solar system would likely survive intact, though it might be flung into a different orbit, perhaps ejected to the outskirts of the new merged galaxy. If humans are still around in 4 billion years, they'd witness a spectacular light show in the sky, but the sun and planets would carry on. Stepping back from the future, let's consider the Milky Way as it exists right now. The galaxy is a dynamic, living system. Stars are born in clouds of gas and dust, primarily in the spiral arms where material is densest. They live for millions or billions of years, depending on their mass. Eventually they die, some quietly fading away, others exploding as supernovae. When stars die, they return material to the interstellar medium, gas and dust enriched with heavy elements forged in their cores. This enriched material becomes part of new clouds, which form new stars. The cycle continues, generation after generation. The Milky Way's star formation rate has varied over its history. Billions of years ago, the rate was much higher. The galaxy was actively building its stellar population. Over time, the rate has declined. Today, the Milky Way forms roughly 1 or 2 solar masses worth of new stars per year. That might sound like a lot, but spread across the entire galaxy, it's relatively modest. Many of the giant molecular clouds where stars form lie in the spiral arms, particularly in regions like the Orion Molecular Cloud Complex, visible from Earth as the Orion Nebula. Star formation doesn't happen uniformly across the galaxy. It's concentrated in certain regions, particularly where spiral arms compress the interstellar medium. The spiral arms themselves are fascinating structures. For a long time, astronomers debated whether they were permanent features or transient patterns. Current evidence suggests they're density waves, regions where stars and gas temporarily bunch together as they orbit. Think of a traffic jam on a circular highway. Cars enter the jam, slow down, then exit on the other side. The jam itself, the region of higher density, moves around the highway at a different speed than the cars. Similarly, spiral arms are patterns that rotate through the galaxy, with stars passing in and out of them. The Milky Way has 4 major spiral arms: the Scutum Centaurus arm, the Carina Sagittarius arm, the Perseus arm, and the Norma arm. There are also smaller arm segments, including the Orion spur where our solar system resides. The exact structure of these arms is still being mapped. It's difficult to determine the galaxy's shape from inside it, like trying to map a forest while standing among the trees. Dust and gas block our view in visible light, forcing astronomers to rely on radio and infrared observations to peer through the obscuration. The central region of the galaxy, the bulge, is particularly difficult to study. Dense clouds of dust lie between us and the center, absorbing visible light. But radio waves and infrared light can penetrate. These observations reveal that the bulge isn't spherical, it's elongated, bar-shaped. The Milky Way is a barred spiral galaxy. A massive bar of stars extends through the center, roughly 10,000 light-years long. This bar rotates as a solid structure, taking about 160 to 180 million years to complete one rotation. The bar plays a crucial role in the galaxy's evolution. It funnels gas from the outer disk toward the center, feeding star formation in the central regions and providing material that can fall toward the supermassive black hole. Barred structures are common in spiral galaxies. Over 2/3 of spirals have bars. The bars can be stable for billions of years, though they can also dissolve and reform. The Milky Way's bar may have formed a few billion years ago, though its exact age is uncertain. At the very center, 26,000 light-years away, sits Sagittarius A star, the supermassive black hole we discussed earlier. Despite its enormous mass, over 4 million times the Sun's mass, Sagittarius A star is relatively quiet. It's not actively consuming large amounts of matter. Most supermassive black holes in galaxy centers are similarly dormant, but there's evidence that Sagittarius A star was more active in the past. Observations have found structures in the galactic center that look like remnants of past outbursts, bubbles of hot gas extending thousands of light-years above and below the disk. These Fermi bubbles, named after the telescope that discovered them, might be echoes of a time when the black hole was feeding more vigorously, perhaps a few million years ago. The Milky Way is not a static structure frozen in time. It's evolving, changing, growing. It continues to accrete gas from the intergalactic medium, fuel for future star formation. It continues to absorb smaller satellite galaxies, adding their stars to its halo. The disk warps and ripples as gravitational interactions stir its structure. Stars are born and die, enriching the gas with heavier elements. The supermassive black hole at the center occasionally flares to life when material falls into it. And through all of this, the galaxy rotates. The Sun completes one orbit every 225 million years, a cosmic year. Since Earth formed 4.5 billion years ago, we've made roughly 20 trips around the galactic center. During that time, the galaxy has changed. Stars that existed when Earth was young have died. New stars have been born. The spiral arms have shifted. The galaxy we orbit now is not quite the same galaxy that existed when life first appeared on Earth. Understanding the Milky Way means understanding our place in the universe. This galaxy is our home on the largest scale. Every atom in your body was forged in stars that lived and died in this galaxy. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it came from stellar furnaces, scattered into space when those stars exploded, then gathered into new clouds that formed our solar system. You are made of stardust, quite literally. The Milky Way built you from its own substance, assembled your atoms over billions of years through cycles of stellar birth and death. The galaxy will continue long after we're gone. Stars will keep forming, keep dying, keep enriching the interstellar medium. The spiral arms will keep turning. The dark matter halo will keep holding everything together through invisible gravity. In 4 or 5 billion years, the Milky Way might collide with Andromeda, or it might not. Either way, galaxies will continue their slow cosmic dance, driven by gravity across vast expanses of space and time. Right now, as you lie here, the galaxy is all around you. You're inside it, part of it. The stars you see at night, every single one, belongs to the Milky Way. The faint band of light stretching across a dark sky, that's our view of the galactic disk from inside. We're looking through the thickness of the disk, seeing countless distant stars blended together into a glowing river of light. The Milky Way isn't just out there in space, it's here, encompassing you, the ground beneath you, the air you breathe. You're rotating with it, orbiting the galactic center at hundreds of kilometers per second. You're moving through dark matter right now, countless invisible particles passing through your body every moment. You're part of something vast, ancient, and ongoing. A galaxy among billions, yet unique in detail, shaped by its particular history of mergers and star formation and dark matter distribution. That's the Milky Way, our galaxy, our cosmic home, still revealing its secrets after centuries of study. The space between those stars is not empty. It never was. Astronomers call it the interstellar medium, and it fills everything. Every gap, every void, every seemingly blank stretch of darkness. It's mostly hydrogen, the universe's most abundant element, drifting in its neutral form. Some of it clumps into vast molecular clouds, dense enough to block light, cold enough to slow atoms to a crawl. Other regions are hot and diffuse, heated by shock waves from exploding stars or radiation from nearby stellar nurseries. The interstellar medium is where stars are born, where they die, where they scatter their ashes back into the cosmic cycle. Without it, the Milky Way would be sterile, a collection of aging stars slowly burning out with no replacements. But because of this gas, this dust, this thin material spread across light years, the galaxy stays alive. New stars condense from it, planets form within it, life emerges from the heavy elements it carries. You can't see most of it. The hydrogen is invisible to human eyes. The dust blocks visible light rather than emitting it. But astronomers have learned to observe the interstellar medium in wavelengths our eyes can't detect. Radio telescopes pick up the faint signal of neutral hydrogen. a specific wavelength of 21 centimeters that penetrates dust clouds and reveals the galaxy's hidden structure. Infrared detectors see through the obscuring dust to the stars and clouds beyond. X-ray telescopes spot the hottest regions where supernova shockwaves have heated gas to millions of degrees. Each wavelength reveals a different layer of the same material, building a complete picture of what fills the space between stars. The density varies wildly. In the coldest molecular clouds, you might find thousands of hydrogen molecules per cubic centimeter, dense by interstellar standards, though still far emptier than any vacuum we can create on Earth. In the hot, ionized regions between spiral arms, the density drops to less than 1 atom per cubic centimeter. That's almost nothing, a near-perfect vacuum, yet it's still there, still part of the galaxy's structure. The interstellar medium accounts for roughly 10% of the Milky Way's visible mass. The rest is stars. But that 10% matters enormously because it's the raw material for everything that comes next. Every star that will ever form, every planet that will ever orbit, every molecule that might one day become part of something alive, it all starts here, in this thin gas drifting between the stars. Dark matter surrounds all of it. The entire galaxy sits inside a massive halo of invisible particles that don't interact with light or normal matter except through gravity. This dark matter halo extends far beyond the visible disk, reaching nearly 2 million light-years from the galactic center. It's not a thin shell, but a diffuse sphere, densest near the center and gradually thinning toward the edges. Most of the Milky Way's mass is dark matter, somewhere between 85 and 90%. The stars, gas, dust, planets, everything we can see or detect directly represents only a small fraction of what's actually there. The galaxy would fly apart without this invisible scaffolding. Stars in the outer regions orbit too fast for the visible mass alone to hold them. They should be flung into intergalactic space, scattered by centrifugal force. But they stay, bound by the gravity of something we can't observe. We still don't know what dark matter is. Decades of experiments have searched for it, looking for subtle interactions, weak signals, any evidence of what these particles might be. Detectors buried deep underground wait for dark matter particles to collide with normal atoms. Particle accelerators try to create dark matter in high-energy collisions. Telescopes map its distribution by observing how it bends light from distant galaxies. But the particles themselves remain elusive, passing through detectors, through Earth, through you, without leaving a trace. Alternative theories suggest we might be wrong about dark matter entirely, that perhaps our understanding of gravity needs adjustment instead. But those theories struggle to explain all the observations as cleanly as dark matter does. For now, the invisible halo remains the best explanation, a massive presence we infer from its effects but cannot directly detect. The Milky Way's formation history is written in its stars. By studying stellar ages, compositions, and orbits, astronomers piece together how the galaxy assembled over billions of years. The oldest stars cluster in the halo and in globular clusters, spherical collections of hundreds of thousands of ancient suns that orbit far from the galactic plane. These stars formed early, when the universe was young and contained almost no elements heavier than helium. Their chemical composition reveals their age. They're metal poor, using the astronomer's definition of metal as anything heavier than hydrogen and helium. The lack of heavy elements tells us these stars formed before many generations of supernovae had enriched the interstellar medium. They're relics of the galaxy's youth, survivors from a time when the Milky Way was still assembling itself from smaller proto-galactic fragments. The disk is younger. Its stars formed more recently from gas enriched by previous stellar generations. They contain higher proportions of carbon, oxygen, iron, all the elements created in earlier stars and scattered by supernova. The thin disk, where the Sun orbits, contains the youngest stars. many still forming today in dense molecular clouds. The thick disk, slightly above and below the thin disk, holds somewhat older stars with intermediate compositions. This layered structure reflects the galaxy's growth over time, each population of stars recording the conditions when it formed. Some stars don't fit the pattern, though. Astronomers have found streams of stars with unusual orbits and compositions, remnants of smaller galaxies that merged with the Milky Way long ago. One such merger, called Gaia Enceladus, after the spacecraft that helped discover it, occurred roughly 10 billion years ago and contributed significantly to the galactic halo and thick disk. The Gaia mission transformed our understanding of the Milky Way's structure and history. Launched by the European Space Agency in 2013, Gaia spent over a decade precisely measuring the positions, brightnesses, and motions of 2 billion stars. That's about 1% of all stars in the galaxy, but it's enough to map large-scale structure and trace stellar motions with unprecedented accuracy. Gaia measured each star's position down to millionths of an arc-second, roughly equivalent to measuring the width of a human hair from 1,000 kilometers away. It tracked how stars move across the sky, revealing their paths through the galaxy. It measured how starlight shifts in wavelength as stars move toward or away from us, providing their velocities along our line of sight. Combined, these measurements place each star in three-dimensional space with a three-dimensional velocity vector, creating a dynamic map of the galaxy in motion. The data revealed surprises. The galactic disk isn't flat but warped, with one edge curving upward and the other downward, like the brim of a hat. This warping was suspected before Gaia, but the mission confirmed it and showed that the warp slowly oscillates over time, precessing like a spinning top. Gaia also discovered a massive wave rippling through the disk, a structure called the Radcliffe wave stretching 9,000 light-years and affecting the motions of stars across a vast region. The cause of this wave remains uncertain, though theories include past interactions with satellite galaxies or internal gravitational instabilities within the disk itself. Gaia found stellar streams, long arcs of stars with similar motions and compositions, marking the paths where smaller galaxies were torn apart and absorbed by the Milky Way. It discovered new asteroids within our solar system, spotted thousands of brown dwarfs, helped identify exoplanets, and even found a massive black hole hiding in the constellation Aquila, less than 2,000 light-years from Earth. The mission completed its observational phase in early 2025, though data analysis will continue for years. 2 major data releases are planned, one around 2026 and another toward the end of the decade. Each release will refine our understanding of the galaxy's structure, stellar populations, and dynamic history. Gaia hasn't just catalogued stars. It's revealed the Milky Way as a dynamic, evolving system shaped by mergers, interactions, and internal processes we're only beginning to understand. The galaxy we thought we knew has been replaced by something more complex, more active, more interconnected than previous observations suggested. Chemical evolution tells another part of the story. Each generation of stars changes the composition of the interstellar medium. Early stars formed from almost pure hydrogen and helium, the only elements created in the Big Bang. They fused hydrogen into helium in their cores, then helium into carbon and oxygen as they aged. The most massive early stars continued fusing heavier elements, building up layers of silicon, magnesium, neon, finally iron at their cores before collapsing in supernova explosions. Those explosions scattered the newly created elements into space, enriching the gas from which the next generation of stars would form. Each cycle added more heavy elements. By the time the Sun formed 4.5 billion years ago, the interstellar medium contained enough carbon, oxygen, nitrogen, silicon, iron, and other elements to build rocky planets and eventually life. The pattern of chemical enrichment varies across the galaxy. Stars near the galactic center, where star formation has been more intense, tend to be more metal-rich than stars in the outer disk or halo. Older stars everywhere are metal-poor compared to younger ones. By measuring a star's composition, astronomers can estimate its age and often determine where in the galaxy it formed. Some stars show unusual abundance patterns, chemical signatures suggesting they formed in environments very different from where they orbit now. These are likely immigrants, stars captured from satellite galaxies during mergers, now drifting through the Milky Way's disk or halo with compositions that mark them as outsiders. Recent research has challenged the assumption that the Milky Way's chemical evolution follows a universal pattern. Simulations of galaxy formation show that different galaxies can develop distinct chemical sequences depending on their merger histories, gas infall rates, and star formation patterns. The Milky Way's particular chemical structure is not a blueprint for all spiral galaxies, but the result of its unique history. Other galaxies should show different patterns, different relationships between age and composition, different distributions of elements. This diversity means we can't simply assume that what we learn about the Milky Way applies everywhere. Each galaxy must be studied individually, its chemical evolution traced through its stellar populations, its history decoded from the elements its stars contain. The bar at the galaxy's center plays a crucial role in this evolution. This elongated structure of stars, extending from the central bulge, rotates more slowly than the stars themselves orbit. The bar channels gas from the outer disk inward, funneling material toward the galactic center where it can fuel star formation or feed the central supermassive black hole. The bar's gravitational influence shapes the spiral arms, helping to maintain their structure and triggering star formation as gas flows through regions of enhanced density. Roughly 30 to 40% of the Milky Way's total stellar mass resides in the galactic bulge and bar, a concentration that significantly affects the galaxy's overall dynamics and evolution. The bar wasn't always recognized as part of our galaxy's structure. For decades, astronomers debated whether the Milky Way had a bar at all. Observing it from our position within the disk proved difficult. Dust obscures the central region's invisible light, and the bar's orientation, viewed nearly end-on from Earth, made it hard to distinguish from a simple bulge. Confirmation came from infrared surveys that could peer through the dust, revealing the elongated distribution of stars characteristic of a barred spiral. Now we know that barred spirals are common, making up more than 2/3 of all spiral galaxies. The proportion has changed over cosmic time, with bars becoming more common as the universe has aged and galaxies have matured. The Milky Way fits this pattern, a mature spiral galaxy with a prominent bar influencing its structure and evolution. That's the galaxy we live in, complex, dynamic, shaped by billions of years of star formation, mergers, and gravitational interactions. It's not a static structure, but an evolving system, constantly changing on timescales too long for human lifetimes to perceive directly. The stars we see tonight are not the same stars that shone when life first emerged on Earth. The spiral arms have shifted, the chemical composition of the interstellar medium has changed, satellite galaxies have been absorbed and torn apart. The galaxy is different now than it was then, and it will be different again billions of years from now. The galaxy's future isn't just written in its past. It's being written now, in the slow gravitational dance with its neighbors, in the streams of gas falling inward from intergalactic space, in the ongoing consumption of smaller satellite galaxies. The Milky Way belongs to a cosmic neighborhood called the Local Group, a collection of more than 50 galaxies bound together by gravity across a region several million light-years across. Most of these galaxies are small, dwarf galaxies containing just millions or billions of stars, rather than the hundreds of billions found in larger spirals. But two galaxies dominate the Local Group by mass and size: the Milky Way and Andromeda. Andromeda lies about 2.5 million light-years away, visible to the naked eye from dark sites as a faint smudge in the constellation it's named for. It's larger than the Milky Way, containing perhaps 1 trillion stars compared to our few hundred billion. though recent measurements suggest the mass difference might be smaller than once thought, and it's moving toward us. The light from Andromeda shows a blue shift, indicating it's approaching at roughly 110 kilometers per second. For decades, astronomers have predicted that this motion would inevitably lead to a collision, a dramatic merger that would reshape both galaxies into a single elliptical system, sometimes called Milky Way. But recent research challenges that certainty. New calculations incorporating the latest data from Gaia and Hubble, along with accounting for the gravitational effects of other nearby galaxies, paint a more nuanced picture. There's only about a 50-50 chance the collision will actually occur within the next 10 billion years. The trajectories of both galaxies are influenced by more than just their mutual gravitational attraction. The Large Magellanic Cloud, a satellite galaxy of the Milky Way, has enough mass to affect both galaxies' paths. Its orbit runs perpendicular to the line between the Milky Way and Andromeda, and its gravitational influence may nudge the two spirals onto trajectories that miss each other entirely, or at least delay any collision far into the future. If the collision does happen, it won't be sudden or catastrophic in the way we might imagine. Individual stars are separated by such vast distances that actual stellar collisions would be extraordinarily rare. Stars from both galaxies would pass by each other like ghosts, their paths altered by gravitational interactions, but rarely touching. What would change is the overall structure. The orderly spiral patterns would be disrupted, twisted, and eventually destroyed. Stars would be flung onto new, more chaotic orbits. Some might be ejected entirely, cast out into intergalactic space. The disks would merge, the gas clouds would collide and trigger bursts of new star formation, and over hundreds of millions of years, the combined system would settle into a new configuration, probably an elliptical galaxy without the spiral arms or disk structure that characterize both galaxies today. The central supermassive black holes would eventually merge too, after spiraling inward through the combined galaxy in a process that could take hundreds of millions of years. When they finally came together, the merger would release an enormous burst of gravitational waves, ripples in space-time that would propagate outward at the speed of light, carrying energy away from the system. But all of this, if it happens at all, lies billions of years in the future. The Sun will have exhausted its hydrogen fuel and expanded into a red giant long before any collision occurs. Earth, if it still exists, will have been sterilized or consumed. The collision of galaxies is a cosmic event, but one that plays out on timescales that dwarf the entire history of complex life on our planet. Closer to home, the Milky Way's satellite galaxies tell their own stories. The Large and Small Magellanic Clouds are the most prominent, visible to the naked eye from the southern hemisphere as hazy patches of light. They're irregular dwarf galaxies, lacking the organized structure of spirals, and they orbit the Milky Way on paths that bring them relatively close. The Large Magellanic Cloud lies about 160,000 light-years away, close enough that it's gravitationally bound to the Milky Way, and close enough that tidal forces are beginning to distort its shape. Star-forming regions blaze throughout the cloud, including the Tarantula Nebula, one of the most active stellar nurseries in the entire local group. The Magellanic Clouds aren't permanent companions. Their orbits are decaying, drawn inward by the Milky Way's gravity. Eventually, they'll be torn apart and absorbed, their stars scattered throughout the galactic halo, their gas mixed into the Milky Way's disk. This process is already underway. Streams of gas and stars stretch between the clouds and the Milky Way, forming structures called the Magellanic Stream and the Leading Arm. These are tidal tails, material pulled from the clouds by gravitational interactions, now drifting through space on trajectories that will eventually merge them with the larger galaxy. Other satellite galaxies are further along in this process. The Sagittarius Dwarf Elliptical Galaxy is being actively consumed right now. Discovered only in the 1990s, This small galaxy lies on the opposite side of the Milky Way's center from us, largely hidden behind the bright bulge and thick dust lanes. Its orbit takes it through the Milky Way's disk, and each passage strips away more of its stars. Long streams of debris trace its orbital path, wrapping around the galaxy like ribbons. These stellar streams are fossils of past interactions, the remnants of a galaxy that's been torn apart by tidal forces. In a few billion years, the Sagittarius dwarf will be gone entirely, its stars mixed into the Milky Way's halo, indistinguishable from the billions of other stars that orbit high above and below the galactic plane. This consumption of smaller galaxies isn't unusual. It's how large galaxies grow. The Milky Way has absorbed dozens of smaller systems over its history, each one contributing stars, gas, and dark matter to the growing whole. Evidence for these ancient mergers comes from stellar streams and from careful analysis of stellar populations. Stars with unusual chemical compositions or strange orbital motions often turn out to be the descendants of long-destroyed dwarf galaxies. By studying these stars, astronomers can reconstruct the merger history of the Milky Way, tracing back through billions of years to identify when different satellite galaxies were consumed. One particularly significant merger, sometimes called the Gaia-Enceladus event, occurred roughly 10 billion years ago. A dwarf galaxy comparable in mass to the small Magellanic Cloud collided with the young Milky Way, and the merger was violent enough to profoundly affect the galaxy's structure. Many of the stars in the thick disk and halo likely originated in this merger. The collision stirred up the existing disk, heating it and puffing it into a thicker structure, while the stars from the dwarf galaxy were scattered onto chaotic orbits throughout the halo. This event may have been one of the most important in shaping the modern Milky Way, a cosmic collision that helped build the galaxy we live in today. Understanding these mergers requires tracing the motions of millions of stars backwards through time, and that's exactly what Gaia has enabled. By measuring precise positions and velocities for billions of stars, Gaia has allowed astronomers to rewind the clock, calculating where stars were in the past and identifying groups that move together, suggesting they share a common origin. This technique has revealed numerous stellar streams and identified stars that likely came from specific dwarf galaxies. It's rewriting our understanding of galactic evolution, showing that the Milky Way isn't a primordial structure that formed in isolation, but the product of countless mergers and interactions. The galaxy's dark matter halo extends far beyond the visible stars. Recent measurements suggest it reaches outward nearly 1 million light-years from the galactic center, making the true diameter of the Milky Way close to 2 million light-years. That's vastly larger than the 100,000 light-year diameter of the visible disk. Most of the galaxy's mass resides in this invisible halo, dark matter that doesn't emit or absorb light, but makes its presence known through gravity. The nature of dark matter remains one of physics' deepest mysteries. We know it's there because of how it affects the motion of stars and gas. The rotation curve of the galaxy, the relationship between distance from the center and orbital speed, stays flat far beyond where visible matter ends. Stars in the outer regions orbit just as fast as those closer in, which shouldn't happen if only the mass we can see is present. The gravitational pull should weaken with distance, causing outer stars to orbit more slowly. Instead, they maintain their speed, indicating enormous amounts of unseen mass distributed throughout a vast halo. What is this dark matter? We don't know. It doesn't interact with electromagnetic radiation, so it can't be made of ordinary atoms. It doesn't emit light, doesn't absorb it, doesn't scatter it. It just pulls through gravity. Physicists have proposed numerous candidates, from exotic particles created in the early universe to modifications of our understanding of gravity itself. But so far, none have been conclusively detected or proven. Dark matter remains invisible, pervasive, and essential. the hidden scaffolding that holds galaxies together and shapes the large-scale structure of the universe. The Milky Way's dark matter halo isn't smooth or uniform. Simulations suggest it's filled with substructure, clumps and streams of dark matter created by the same mergers and interactions that built the visible galaxy. When a dwarf galaxy falls into the Milky Way, it brings its own dark matter with it. That dark matter doesn't mix instantly, but can persist as a distinct stream or clump for billions of years, gradually dispersing through gravitational interactions. These dark matter structures are invisible, but they leave signatures in the distribution and motion of stars. By studying how stars move through the halo, astronomers can infer the presence and properties of dark matter substructures, mapping the invisible scaffolding that underlies everything we see. This understanding connects to broader questions about how galaxies form and evolve. The current model, called Lambda CDM, describes a universe dominated by dark energy and cold dark matter. In this picture, galaxies form from the bottom up, starting with small fluctuations in the early universe that gravity amplifies over time. Dark matter clumps first, creating gravitational wells that attract ordinary matter. Gas falls into these wells, cools, and begins forming stars. Small galaxies form first, then merge to create larger ones in a hierarchical process that continues to the present day. The Milky Way fits this picture. Its halo is filled with the debris of past mergers, stellar streams, and substructures that mark where smaller galaxies were consumed. Its disk formed gradually as gas settled into a rotating plane, with star formation proceeding over billions of years. The central bar developed later, probably within the last few billion years, as gravitational instabilities in the disk caused stars to organize into an elongated structure. The spiral arms are even more transient, lasting perhaps only 100 million years before dissolving and reforming, shaped by density waves that propagate through the disk. This is a dynamic picture of galactic evolution, very different from older models that treated galaxies as static objects. The Milky Way is constantly changing, accreting new material, consuming satellites, forming stars, and evolving its structure. The galaxy today is different from the galaxy of 1 billion years ago, and it will be different again 1 billion years from now. We're seeing a snapshot of an ongoing process, one moment in a story that stretches from the early universe to the distant future. The stars around us are part of that story, temporary arrangements in a system that never stops moving, never stops changing, never reaches a final stable state. Word count, 2083, Part 5. The living galaxy. The future isn't set in stone. Even with all our measurements, all our sophisticated models, the Milky Way's destiny remains uncertain. Will it collide with Andromeda or pass by like ships in the cosmic night? Will the spiral arms persist or dissolve into chaos? Will new satellite galaxies fall in and reignite star formation? Or will the galaxy slowly fade as its gas supply dwindles? We can make predictions, but the universe has a way of surprising us. Every major astronomical discovery of the past century has revealed something we didn't expect, something that challenged our assumptions and forced us to rethink what we thought we knew. What we can say with certainty is that change is constant. The galaxy won't remain as it is. Stars will continue their slow orbits around the center. New stars will form in dense molecular clouds, while old ones exhaust their fuel and die. The interstellar medium will be stirred by stellar winds and supernova explosions. Dark matter will continue its invisible dance, holding everything together through gravity alone. The bar will keep rotating, funneling gas toward the center. The spiral arms will sweep through the disk, triggering bursts of star formation wherever they pass. And slowly, imperceptibly on human timescales, the overall structure will evolve. The Milky Way is not a thing, but a process. It's not a static object frozen in space, but a dynamic system constantly reshaping itself. Every element of it is in motion. The stars orbit at different speeds depending on their distance from the center, The gas flows inward along spiral arms and outward in fountains driven by stellar feedback. Dark matter streams through the halo, invisible currents shaped by ancient mergers. Even the supermassive black hole at the center, sleeping now, will occasionally wake when material drifts close enough to be captured. Nothing stays still. Nothing remains unchanged. This constant motion makes the galaxy more like a living organism than a machine. Not alive in the biological sense, obviously, but alive in its complexity, its interconnectedness, its responsiveness to internal and external forces. When a satellite galaxy passes too close, the Milky Way's gravitational field responds, warping and stretching the intruder until it's torn apart. When massive stars explode, the energy they release heats surrounding gas, preventing it from collapsing immediately into new stars, regulating the pace of star formation. When gas flows inward along the bar, it can trigger bursts of activity in the central regions. The galaxy has feedback mechanisms, regulatory systems, cycles of activity and quiescence that play out over millions or billions of years. Understanding these processes requires looking at the galaxy, not just as a collection of stars, but as an ecosystem. Stars are born from gas clouds. They live for varying lengths of time, depending on their mass. They die and return material to the interstellar medium, enriched with heavy elements forged in their cores. That enriched material becomes part of new clouds, which form new stars, continuing the cycle. The system is self-sustaining, as long as fresh gas continues to flow in from outside. Without that inflow, star formation would gradually decline as the available gas is converted into stars or ejected by stellar feedback. The galaxy would age, its population dominated by older, cooler stars, the bright blues and whites of youth replaced by the yellows and reds of stellar middle age. But fresh gas does flow in. Observations show streams of neutral hydrogen falling into the galaxy from the cosmic web, the large-scale structure of dark matter filaments that connects galaxies across the universe. This gas replenishes what's lost to star formation and galactic winds, maintaining a reservoir of raw material for future generations. The inflow rate varies over time, influenced by the gravitational environment and the galaxy's own rotation. During periods of high inflow, star formation increases. When the flow diminishes, star formation declines. The galaxy breathes, inhaling gas from intergalactic space and exhaling energy through stellar winds and supernovae. This breathing has a rhythm, though not a regular one. There's evidence for periodic bursts of star formation in the Milky Way's past, episodes when conditions favored rapid conversion of gas into stars. Some of these bursts correlate with major merger events. When a satellite galaxy falls in, it brings gas with it, and the gravitational disruption can trigger widespread star formation throughout the disk. Other bursts may be internally driven, the result of density waves in the disk growing strong enough to compress gas clouds beyond their stability threshold. The galaxy's star formation history isn't smooth but punctuated, a series of active episodes separated by quieter periods. Reading this history requires studying stellar populations. Stars are fossils of the conditions when they formed. Their ages can be estimated from their colors and brightnesses. Their chemical compositions reveal the enrichment level of the interstellar medium at their birth. By mapping these properties across the galaxy, astronomers reconstruct when and where different populations formed. The thick disk stars, for instance, formed mostly between 8 and 12 billion years ago, during a period of intense activity, possibly triggered by mergers. The thin disk stars are younger, formed over the past 8 billion years from progressively more enriched gas. The halo contains the oldest stars, some nearly as old as the universe, formed before the disk had even assembled. This layered structure tells a story of hierarchical assembly. The Milky Way didn't form all at once, but built up gradually from smaller pieces. The first stars formed in small proto-galactic fragments, scattered across a region of space. These fragments merged, combining their stellar populations and dark matter halos. As the system grew, gas settled into a rotating disk, where new stars continue to form. The disk grew from the inside out, with the inner regions forming stars first and the outer regions assembling later. Meanwhile, the halo accumulated stars from disrupted satellites, building up over billions of years through ongoing mergers. This process continues today. The Sagittarius dwarf is being torn apart right now, its stars streaming around the galaxy in long arcs. The Magellanic Clouds are slowly falling inward, their eventual fate to be absorbed and scattered throughout the Milky Way's structure. Other small satellites orbit in the halo, some already identified, others possibly still undiscovered. Each one will eventually be consumed, adding its mass to the growing galaxy. The Milky Way is still assembling, still growing, still in the process of becoming whatever it will ultimately be. But growth can't continue forever. The local group, the collection of galaxies that includes the Milky Way, Andromeda, and dozens of smaller systems, is gravitationally bound. That means it's isolated from the general expansion of the universe. While distant galaxies recede as space expands, the members of the local group remain gravitationally tied together. Over time, this group will continue to merge and consolidate. Smaller galaxies will be absorbed by larger ones. Eventually, only one or two massive galaxies will remain, the combined product of all the mergers. If the Milky Way and Andromeda do collide and merge, the resulting system will dominate the local group, possibly absorbing all remaining satellites over the following billions of years. That future galaxy will be very different from the Milky Way we see today. The merger will destroy the spiral structure, scattering stars onto chaotic orbits and forming an elliptical galaxy with no disk, no spiral arms, no organized rotation. Star formation will spike during the collision as gas clouds collide and compress, then gradually decline as the available gas is consumed or heated to temperatures too high for star formation. The merged galaxy will be larger, more massive, and redder than either progenitor, dominated by older stellar populations with little ongoing starbirth. But that's billions of years away. For now, the Milky Way remains a spiral, its disk rotating steadily, its spiral arms sweeping through space, its star formation continuing at a modest but steady rate. We live in what might be called the galaxy's middle age. The early period of rapid assembly and intense star formation has passed. The disk has settled into a relatively stable configuration. Star formation continues, but at a lower rate than in the past. The galaxy has matured, evolved from the chaotic activity of youth into a more sedate adulthood. But it's not static. It's still active, still dynamic, still capable of surprise. Consider what we've learned just in the past decade. Gaia revealed that the disk is warped and rippling, shaped by forces we're still working to understand. Observations found evidence of a massive wave structure extending across tens of thousands of light years. Studies of stellar streams uncovered the remnants of numerous ancient mergers. Measurements of dark matter distribution showed substructure in the halo, clumps and streams left over from past satellite captures. Chemical abundance studies challenged assumptions about how galaxies evolve, and the realization that the Andromeda collision might not happen, or might happen much later than expected, upended predictions about the galaxy's long-term future. Each discovery raises new questions. What causes the disk to warp? Is it interactions with satellite galaxies, or internal dynamics, or something else? What triggered the formation of the Radcliffe wave? How many ancient mergers contributed to the Milky Way's assembly, and can we identify them all from stellar streams? What is dark matter, and why does it clump the way simulations predict? Does the Milky Way's chemical evolution follow a unique path, or are there common patterns shared by similar galaxies? The more we learn, the more we realize how much remains unknown. This is the nature of science. Every answer opens new questions. Every discovery reveals new mysteries. The Milky Way seemed relatively simple a century ago, a nebulous band of stars whose structure was poorly understood. Now we know it's a barred spiral galaxy containing hundreds of billions of stars, embedded in a massive dark matter halo, surrounded by satellite galaxies, connected to neighboring systems through gravitational interactions, and constantly evolving through star formation, mergers, and internal dynamics. But this deeper understanding hasn't eliminated mystery. It's revealed how complex the system actually is, how many factors influence its evolution, how much we still need to learn. The galaxy will outlast humanity by an unimaginable span. Even if our species survives for millions of years, even if we spread throughout the galaxy and become a truly spacefaring civilization, we'll witness only the briefest moment of the Milky Way's existence. The galaxy was ancient when Earth formed. It will continue long after our sun dies. Stars will keep forming, keep dying, keep enriching the interstellar medium. The spiral arms will keep turning. The bar will keep rotating. Satellites will continue to fall in and be absorbed. And eventually, billions of years from now, the galaxy may merge with others, transforming into something new. But right now, in this moment, the Milky Way is home. Every star you can see with your naked eye belongs to it. Every constellation, ancient civilizations named and navigated by. Every meteor that streaks across the night sky. Every planet wandering against the fixed stars. All of it part of this one galaxy. We're embedded in it, moving through it, made from its material. The atoms in your body were forged in stars that lived and died in this galaxy. The oxygen you're breathing, the carbon that forms your cells, the calcium in your bones, all of it cycled through stellar furnaces, scattered by supernovae, gathered into molecular clouds, incorporated into a new solar system. You are made of the Milky Way in the most literal sense. You're not just in the galaxy, you're of it, built from its substance, shaped by its history, and you're part of its future too. Everything you do, every breath you take, every thought you have, happens within this galaxy. Your existence adds infinitesimally to its total mass. The light you emit as thermal radiation becomes part of the galaxy's energy budget. When you die, your atoms will return to Earth, and eventually, on timescales so long they're almost meaningless to contemplate, some of those atoms may be recycled into space, joining the interstellar medium, perhaps becoming part of future stars. You're a temporary arrangement of galactic material, a pattern that holds for a few decades before dissolving back into the whole. That might sound bleak, but it's not. It's connection. You're not separate from the universe, observing it from outside. You're part of it, woven into its fabric, as much a natural phenomenon as a star or a planet or a grain of dust drifting between solar systems. The same physical laws govern your body and distant galaxies. The same elements make up your cells and nebulae. The same forces shape your existence and the evolution of cosmic structure. There's no division between you and the galaxy. You're continuous with it, an expression of it, a way the Milky Way has become aware of itself. So when you look up at the night sky and see that faint band of light stretching overhead, remember, you're not looking at something distant and separate. You're looking at your cosmic home from the inside. Every photon entering your eye traveled from distant stars, carrying information about objects you'll never visit, but to which you're forever connected. You're seeing the galaxy's structure, its spiral arms and dust lanes, its billions of stars arranged in patterns shaped by gravity and motion. And you're seeing it with eyes made from atoms those same stars created, using a brain built from stellar ashes, powered by energy that traces back through countless transformations to nuclear fusion in the sun's core. The Milky Way is vast, ancient, complex, and beautiful. It's a river of stars flowing through space, a cosmic ecosystem where matter cycles through generations of stellar birth and death, a dynamic structure constantly reshaping itself through processes that unfold over millions and billions of years. It's a barred spiral galaxy, one of hundreds of billions in the observable universe, yet unique in its particular arrangement of stars and gas and dark matter. It's our home, the only galaxy we'll ever truly know from the inside, the cosmic address that defines our place in the universe, and it's still revealing its secrets. Despite centuries of observation, decades of space missions, and the analysis of billions of stars, we've only scratched the surface of understanding. The Milky Way remains mysterious in fundamental ways. We don't know what most of its mass is made of. We can't predict its long-term future with certainty. We're still mapping its structure, still discovering ancient stellar streams, still finding new satellites, still uncovering evidence of past collisions. The galaxy holds stories we haven't yet read, written in starlight and encoded in the motions of billions of suns. Those stories connect to our own. The Milky Way's history is humanity's history too. The elements that make life possible were created in stellar cores. The solar system formed from material enriched by previous generations of stars. The sun's location between major spiral arms may have provided a stable environment where complex life could evolve without too much disruption from nearby supernova or stellar encounters. We exist because the galaxy evolved in a particular way, with a particular history of star formation and chemical enrichment. Different circumstances might have produced a different galaxy, one less hospitable to life, or one where life formed, but in ways we can't imagine. We're fortunate to live when we do, in a universe old enough for complex chemistry, but young enough for stars to still shine brightly. Billions of years from now, the universe will be darker, colder, more diffuse. Star formation will decline as galaxies exhaust their gas supplies. Eventually, the last stars will flicker out, leaving behind only remnants. White dwarfs, neutron stars, black holes, slowly cooling through eras so long that billions of years seem like seconds by comparison. The universe's long future will be one of increasing entropy, structure dissolving, energy dispersing, everything gradually approaching thermal equilibrium in a state sometimes called heat death. But that's unimaginably far ahead. Right now, the universe is bright, stars are being born, galaxies are evolving, complexity is increasing, life, at least on Earth and possibly elsewhere, is flourishing. This is a special time, cosmologically speaking, a brief window in the universe's history when conditions favor structure, activity, and the emergence of complexity. We're living in that window, experiencing the universe when it's most interesting, most dynamic, most full of potential. The Milky Way embodies all of that. It's a structure born from the early universe's tiny fluctuations, grown through billions of years of gravitational assembly, shaped by countless mergers and interactions, populated by hundreds of billions of stars in various stages of their life cycles, surrounded by invisible dark matter that holds everything together, constantly exchanging material with its environment, slowly evolving toward an uncertain future. It's complex beyond full comprehension, beautiful in its structure and motion, ancient yet still changing, vast yet intimately connected to the smallest details of our existence. That connection is what makes astronomy meaningful. We're not studying distant objects unrelated to our lives. We're studying our origins, our context, our home. Every fact about the Milky Way is also a fact about where we came from and where we're going. The galaxy's chemical evolution explains why Earth has the elements necessary for life. Its structure explains why our solar system occupies a relatively safe location. Its history of mergers and star formation shaped the environment in which we evolved. Understanding the galaxy means understanding ourselves as products of cosmic processes, temporary expressions of matter and energy, arranged in patterns that can think and wonder and ask questions about the universe. So as you drift towards sleep, let your thoughts expand outward. Picture the Milky Way as it truly is, not just the band of light visible from Earth, but the entire three-dimensional structure. The flat disk with its spiral arms and bar, the spherical halo of ancient stars and dark matter, the satellite galaxies orbiting like moons around a planet, the streams of stars marking past mergers, the clouds of gas where new stars are forming, the supermassive black hole at the center, patiently waiting, the invisible dark matter holding everything together. Picture all of it rotating slowly, majestically, a cosmic pinwheel turning in the darkness of intergalactic space. And then zoom in, past the outer halo, through the thick disk, into the thin disk where most stars reside. Follow the Orion spur, that minor spiral arm where our solar system orbits. Find the sun, one ordinary yellow star among billions. Approach Earth, that small blue world where life emerged and evolved, and eventually developed the capacity to look outward and understand its cosmic context. Come back to yourself, lying here, breathing slowly, thoughts drifting. You're part of all of it, made from it, shaped by it, connected to it in ways both obvious and subtle. The galaxy continues its ancient rotation. Stars drift along their orbits. Gas clouds collapse and form new suns. Old stars die and scatter their ashes. The interstellar medium churns and mixes. Dark matter streams through the halo. The bar rotates at the center. Spiral arms sweep through the disk. And somewhere in the quiet space between major structures, a yellow star orbits peacefully, carrying a small planet where beings made of stardust contemplate the cosmic river that made them possible. Sleep well in the knowledge that you're home, not just on Earth, but in the Milky Way, that vast spiral of light and darkness where matter has arranged itself into stars and planets, and somehow into you.